Hello, everyone. I'm very happy to invite Dr. Junwen ZHONG from the University of Macau to give us a really interesting talk on flexible actuators and sensors. I've been an old friend with Professor ZHONG for a long time. He has joined the University of Macau since 2020, and before that, he obtained his PhD from Huazhong University of Science and Technology. He was a postdoc researcher in University of California, Berkeley, since from 2016 to 2019, over which period we had good collaborations and well, affected a lot on my research interests, actually. And then he was a special postdoctoral researcher in Riken, Japan in 2020. Dr. ZHONG has published over 80 research papers, including very prestigious journals like Science Robotics, Nature Communication, Energy and Environmental Science, Advanced Materials, Advanced Functional Materials, and it's a really long list. I don't have to iterate. He has also published 1 US patent, 16 Chinese patent, and 2 book chapters. His work has been widely reported by Science, Nature Nanotechnology, Scientific American, Nature Electronics, and the broad media from all over the world. Let's welcome Professor ZHONG to give us a good talk.
Thanks the invitation from Professor Tao and Professor Ma. Okay, once again, I am Junwen ZHONG from University of Macau. Okay, the topic of the talk today should be flexible electromechanical transducers and the human-machine interactive applications. So in Chinese is 柔性机电转换器件及其人机交互应用. So first I will introduce the background. As you know, why human-machine interaction is a very hot topic now, and is also the important parts of the flexible electronics. Actually, for the electrochemical transducers like sensors, actuators, and soft robotics, they are very important hardware foundations of human-machine interactivity. They play the keywords as the interactive phases, right? Interactive phases. So just like the sensors actuators, they can realize the motions or tactile, the sensing and emulating. And for this soft robotics, they can use to detect the signals and use for the signal transmitting or something like that. Of course, the power source should be another very important component of such human-machine interactive systems. So within the recent years, especially for the most recent 5 years, my research focused on the flexible electromechanical devices, such like the flexible energy harvester, especially that can work in the harsh environment, and the wearable smart sensors for detecting the physiological signals, just like pulse, the temperature, the heartbeat, or something like that. And also the haptic feedback actuator that can provide vibrational information. I think high dimensional rich vibrational information to the human body, right? Just like some pattern information. And also the last one is the bio-inspired tiny robotics, or what we call them electric insects. The first 2 contents belong to the application of sensors, and the next 2 devices belong to the application of actuators. And all these devices are based on the working mechanism of electric induction or the piezoelectric effect. So first I will introduce the electrostatic material we use. The material we use is called, maybe it's not so normal to you guys. It's called electron, or in Chinese, what we call 柱集体. Okay, what is electron? Electron is a piece of dielectric material that can exhibiting a quasi-permanent electrostatic charges. Quasi means half permanent, means that these charges can survive or be held on the electron material for a very, very long time. These charges including the surface charges, space charges, or the dipole charges. And if there's charges on if there's charges on the on the if there's charges on the this surface, okay, if we induce the if there's electron on the backside, if we induce the charges on here, okay, so this is based on the electrostatic induction effect. And electron material actually, you know, the lifetime of these charges will be very, very long. Experimentally observed that the lifetime of the charges on a very typical electron material called the Teflon. You guys what know is Teflon, right? The base material of the non-sticky bowl. Okay, so the lifetime of this material, the charges hold it on a PTFE material can be last for hundreds of years, hundreds of years. And actually, electron material has a very broad application in the past decades, just like the microphone. Actually, the first commercial microphone is the electron microphone, and also use it to some printer or the air filtration or something like that. And if we have electron material that has captured the charges, so this is the base structure of the of our device. Okay, so normally here, we have charge electrode here. So if we have charges captured on the surface, it will induce charges on the top electrode and the bottom electrode. And in a static state, okay, the electrical balance is built. So no charges will flow from between these two electrodes. But when you press it, you reduce the gap D2 or air gap, and then more charges will induce on the bottom electrode, and then the electrical potential balance is broken, and then this unequal electrical balance will drive the electrodes to flow from the bottom electrode to the top electrode. Then we can generate a parent peak. And if you keep pressing it, the balance is achieved again. Okay, and then you release it. This is a reverse process. The reverse process to the pressing process. Then in this way, by pressing and releasing the device, we change the capacitance of this system, and then we drive the mechanical energy will be converted to the alternating electricity signal or energy. So it's just something like this one. When I press it, it light up HST, and when I release the device, it light up the LED is composed of WNAO. So HST is Hua Zhong University of Science Technology. That's my my university. Okay, and so by using this way, by pressing it and releasing it, we break the balance, electrical balance between these two electrodes, and then generating the AC voltage or AC electricity signal or energy. So this is the base working mechanism. But as you know, so our device, highly relied on the electricity charges, right? So when the humidity or in a harsh environment, what will happen to such electrostatic charges? These charges will disappear, right? And then our device will not work again. So, but recently, about 2 years ago, we find a very interesting phenomenon. Is that okay? We find a polymer material called the PMEDSH COP AA polymer. Okay, in this polymer, when this polymer meet the moisture or water molecules, and by this autonomous chemical reactions, we find that the surface potential or the surface charges on this polymer surface will have the oscillation. And it means that by using this material, when it meets the water or moisture, it can generate the electrical charges on the surface. So this is a very interesting phenomenon. And by using this one, we use to construct the electrostatic energy harvester. That can have the stable output under the harsh environment. So this is the base structure of our device. So the yellow color one actually is a gold electrode that with punch holes, and then this punch holes can make the water that can immerse into or goes into the device to meet the polymer surface. And then with this one, okay, the protons or the hydrogen ions will, the concentration will varies, that generating the potential variation. Okay, still remember, if the potential variations happen, okay, then you can drive the electrons to go through the external circuit that can generating the voltage, So very different from the traditional electrostatic device. Our device can work in a very high humid environment, and then it can generate a reasonable electrical output. By using this one, okay, what's the advantage of our this kind of moisture-enabled electrostatic energy harvester? The first advantage is that once triggered by the humidity, it can continuously or stably generating the electrical signal. Okay, you can see that once triggered, it can this energy harvest generating process can last up to about 10,000 seconds. Okay, maybe I remember is 15,000 seconds. That's a very long process. Okay, and also another one is that the energy density generating by this kind of moisture-enabled electrostatic generator is very high. Okay, it's very high. So this performance, the general performance of our energy harvester is very outstanding among the reported moisture-enabled energy harvester. So, and this device not only can be used for once, okay, when it's triggered and then dry, this device can continuous work when it meets the moisture again. So we actually not only we test the 3 times, actually we test tens of times, but we just select some data from the 3 times. The performance will not have very big difference. So then in this is a very simple demonstration is that, okay, we connect 5 energy harvesters together to increase the output, especially the output voltage. Then put it in a bath zone. Okay, a bath zone is full of monitor, right? And it can light up some low power conventional electronics, just like an LCD. Okay, so very simple demonstration demonstrating that yes, it can harvest the energy in real application scenarios. So this is the work. And after introducing the electrostatic one, so I actually in recent years actually we focus on more on this kind of new kinds of piezoelectric material, or I think maybe piezoelectric is United States accent, right? Maybe British accent is piezoelectric. Okay, so this kind of material actually indeed is an artificial piezoelectric material, but indeed is still electrostatic material. What we call is called a piezoelectric. Piezoelectric. What is piezoelectric? Piezoelectric is a cellular structure polymers with piezoelectricity. Why it has the piezoelectricity? Because if you look clear here, this is the structure of the very traditional piezoelectric material. It's called cellular polypropylene. Cellular polypropylene. So here there are many air bubbles. This Oliver shape air bubbles with diameter about tens of micrometers, and we have a way to charge it, to make the inner surface the upper layer with positive negative charges and the lower layer with positive charges, or if you reverse the polarization direction, it's also okay. It's also okay. Then one layer of positive charges, one layer of negative charges was this one. It's called electrical dipole, right? I think many of you guys have the experience for doing research on piezoelectricity. Okay, so just like this traditional piezoelectric material like PZT, ZNO, and PVDF. So with this one, okay, because this is air bubble, when you compress it, actually the air bubble structure is ready to be compressed, right? Then we can change the dipole moment. When you change the dipole moment of the piezoelectric material, you can convert the mechanical signal to the electrical signal. So what's the advantage of such new kinds of polymer-based piezoelectric material? The first innovation is that, okay, the DVV value is very high. okay, it can up to about 600 picocoulomb per Newton when you compare to traditional PVDF, PZT, and crazy. Okay, and another one is that actually in deep, this is a foam, right? This is a foam, polymer foam. What's the specific features of polymer foams? The first one is very light because most of the structure is air, and another one is very soft. So this kind of material is light, is soft, it has high electromechanical coupling efficiency. That is very good to be used as wearable electronics. So for this piezoelectric material, or Yuan and me, you know, when we were in UC Berkeley, so we construct such a new type, very high performance piezoelectric material is called sandwich structure piezoelectric material with a high DVV. So the structure is very simple. It's composed of FEP. FEP is a fluorine carbon material that can easily capture charges. And then that's in the spacer we use EcoFlex, so it's very easy to be compressed. So by these electrical and mechanical properties, excellent properties, then we have achieved very high piezoelectric confidence. It can up to about 4,000 picocoulomb per Newton. And this DVP value has also very high stability. So by using this one, okay, we can use it to construct sensors function or actuator function. So in sensor function, I introduced a little just now. Okay, when you compress it and when you swing, you are changing the dipole moment of the electrical dipoles. Then you can convert it to generating the mechanical signal to the electricity, right? When you press it, release it, press it actually very light, okay? And then you can light up the LCD one, okay? And you can see for this real device, you can see that this very air bubble structure. And when used as an actuator, in this condition, we apply the AC voltage, okay? So when we apply AC voltage, it can, you know, change the thickness of the device that generating the vibration. Then the DVP value here, what's the what it can be, what's the benefits when you such high DVP value? It can reduce the drying voltage. Okay, so when you apply voltage, you can see that definitely you can see the vibration, right? The vibration is actually is not so small. You can see it with your eyes. Okay. So after introducing the basic working method, and then I'm introducing the application examples. So the first one is the this is what was finished when I was in Japan. Okay, at that time it was pandemic. So my professor told me, okay, would you please think about an idea that can contribute to the prevention of the pandemic? So okay, right, then I think that we can construct such a smart face mask. Okay, but for the smart face mask, okay, we need to reconstruct or we decide the sensor. So actually, when we breathe, right, we can generate very big airflow. So it means that the sensor must trigger by such weak airflow. Okay, normally the pressure generating by airflow will be below 100 Pascal. That's a very low value. So in order to achieve this requirements, we design such a very actual thin or actual light piezoelectric sensor. Okay, the thickness of such sensor is just about 5 micron, and the weight of such sensor is also very low. You know, it can see that it can stand very well, you know, on the tip of the dandelion, right? And the total weight of this sensor is just about 4.5 milligram. It's very small value. And using then we assemble these sensors into a face mask. And because the output of this face mask, this sensor is also high. Okay, it can up to about this is the real output of the sensor when it was driven by the airflow, you know, from the breathing motions. So these signals can be easily, you know, processed by a very simple circuit and powered by a battery. So we can construct such a system, and these detected signals can be transmitted to cell phone and then out to car. So this is the concept. And this is the specific construction of our system. The breath sensor, can be, persist with a very simple circuit, and then to my cell phone. The whole system, driven power by such a small battery. Actually, if you can remove the package, actually there's a very small battery inside. Okay. Then with this one, the whole smart face mask can work continuously 8 hours. It's totally enough for daily use. Actually, when we wear a face mask, normally we will not wear it for continuous up to 4 or 6 hours. So 8 hours working time is totally enough. And by this one, we can use the cell phone to record different breath conditions, just like normal breath, fast breath, cough, and holding breath or something like that. So this is a video for showing it. Okay, so this is my postdoc. Okay, Zhao Yang now is working in Mapuso, okay, Max Planck Institute. Okay, and here you can see that. Okay, first he breathed normally and can record the breath normal curve. Okay, including the frequency and the amplitude. And now he breathe fast. If breathe fast, of course, the output will be higher. And go back to normal again. And actually, in this app, we decide it can do some simple data processing, just like analyzing some or extracting some brief features, brief features. Yeah, again, and now he is this is coughing, and this is the holding breath. Okay, and then go back to normal again. Yeah, so this video shows that we successfully record the different kinds of breath conditions without such a simple system. And the next work, okay, actually we find that okay, only with that app we can do some simple data processing, but we don't really use it to diagnose some diseases. So the final purpose of our smart face mask project is that we can use this face mask to do some brief illness or respiratory disease detection or diagnosis. So another drawback of our previous face mask is that okay, the sensor is not permeable, right? If you even though the size is not so big, but somehow it will affect the breath smoothly. Okay, so in order to overcome these two things, okay, two drawbacks, we decide such all textile or all fiber-based sensor, Okay, here we use it use the punch paper as electrode and use the PLA to construct the piezoelectric material and use the PLA as a filtration layer. Okay, filtration layer. Then because all the material we use here is eco-friendly material, so including this face mask. Okay, including this face mask. So the whole face mask and the sensors will be degradable. Okay, after maybe about 70 days. And the signals. So this is the device we use. Okay, and then this is the image of the smart face mask. And the signals from this smart face mask can be recorded by the VIII circuit. And then we use the machine learning algorithm, decision tree, to do this brief illness diagnosis. And so this is the real text image of our idea. Okay, we use it to record the data, and then using sensor, then record data and using the algorithm for the analyzing the data. So here in the machine learning, so we do the research in the learning mode or in the training mode. Okay, we use AT data for the texting, and then we do the feature extraction first, and then find some 26 features, and then using these features, we use the left 20 texting data to validate the the training result. And then we can detect three kinds of the brief illness, just like the arrhythmia. You guys know what's arrhythmia? 哮喘, okay. And bronchitis, 支气管炎, and COPD, 呼吸暂停综合症. And the last group is the health people, okay. And then we can, very precisely diagnose these three kinds of illness and the health group. And I think one very important thing I need to mention is that we do this real in the hospital. We connect this data from the real patients from the hospital. Okay. And with this one, we can use this machine learning algorithm, decision tree, to. So this is the matrix, right? This is the actually using. I just select three features, okay, or three maps that can clearly classify these four groups. And the general accuracy for this diagnosing these four groups can up to 95.5%. Okay, especially for distinguishing the health group, it can up to about 100%. And then for the other three groups, okay, because if they have even though they have different brief illness, but the symptoms should be a little similar, right? So there are some faults here. But we are pleased that, okay, the general distinguishing accuracy or diagnosis accuracy is very high. It can up to about 95.5%. So another work about using combining the sensor and the machine learning algorithm example is that, okay, we developed such an untethered patch for wearable smart sensing and image harvesting. So this is the why we call this untethered patch, because in this sensor we use the human body as a signal transmitting pulse or conductive pulse, because actually human body is somehow conducted, right? And in this way we don't use any external wire. We just simply attach the sensor on the finger tip, and the signal generated we transmit it to a circuit that attach with your skin in other parts. So here we do three demonstrations. The first demonstration is object distinguishing combined with the machine learning algorithm. We use this algorithm here we use is called SVM, or support vector machine. In Chinese name, it's called 支持向量机. Okay, and then another demonstration is that, okay, we can code the information by tapping the finger, so we can transmit the wireless information. And the third one, of course, it can make the size of the sensor be larger. And indeed, it's an energy harvester, right? So we attach it on the on the foot, okay, and then when you walk, it can generate the electricity light up the LED. But I have to say, this is just a simple demonstration, right? You cannot really use it as a energy harvester, because the current should go through the human body, so the amplitude of the current should not be too high, or it will hurt people. Right? But normally the amplitude of the current is below 1 milliampere. That's safe. That's okay. So yeah, so here we simply use it as this. We want to more focus on these two applications. So I want to introduce more about the ML mesh assisted object distinguishing. Okay, so here we use this sensor to tap different objects, the surface of different objects, and then we do such an algorithm, machine learning process, and then the object distinguishing overall accuracy for distinguishing about 11 objects can be up to about 94.91%. That's also very high with this one. Okay, so this is our sensor work. Now we want to combine. I think maybe 3 years ago, combining machine learning algorithm with the sensor somehow is new, but now many people are doing that. So we are still finding some novel ways to further improve or go make this such work can go further. For this machine learning assistant wearable sensing system, we also wide review and then published this year. So it could actually for the machine learning assisted system, including 3 steps. One is data connection, another then is data processing analysis, and then data application. So actually has very, now you can see that many kinds of machine learning algorithm has been used to such wearable sensing application. Also, the application is very broad, just like tactile precipitation, gesture recognition, GI analysis, and healthcare, and something like that. Okay, I think that is tending more applications. So if you have interest to learn more about the machine learning wearable sensing system, you can just read our review. Okay. And after talking about the sensors, then I want to talk about the actuators. Okay, this work is actually, this is the first work we published about the application of actuators. Or even though it's actually Ma and me, spend a lot of time, and a lot of effects on this work. Even though finally it's published in Excellent, but we are very proud of this work. Okay, so why we want to develop such an haptic feedback actuator? Because actually the market of haptics is very large. Okay, what is haptics? Okay, so I think if you use the cell phone, right? Okay, that's a setting here. Okay, that's a haptics. And then when you tap the screen, there's something, a vibrational feedback. That is haptic feedback. Okay, that's haptic feedback. But what kind of components that can make you feel the haptic feedback? Actually, it's a linear motor. So when you touch the screen, you think that this position is vibrating. Actually, this is not. The whole screen is vibrating. Okay, or the whole cell phone is vibrating, because this is a rigid one. This is a rigid one. Okay, so what we want to do is that we want to develop the flexible actuators, especially the actuator arrays that can provide strong output. Why strong output? So this is the device, the actuator arrays. The array we developed is a 9 pixels array, and if you it's also based on the sandwich structure piezoelectret I introduced just now. Okay, just now. So there are 2 advantages for this kind of actuator array. The first one is that it can output very good, very high force. This output, when you drive voltage of about 3.3 volt per micrometer, actually, because the thickness of our device is about 150 microns. So the wheel drive voltage is up to 500 volt. But under this condition, okay, the output force can be compared to the vibration mode of the cell phone. So when somebody call you, it's ringing, right? Then you can feel that, okay, this is vibration mode. Okay, cell phone. And this data is texted by Yuan. Okay, at the beginning, because somehow I am not a PhD student in mechanical engineering. He was okay. So he told me how to measure this signal. Still remember when we are in BMC, right? Okay. So this is the first advantage, that it can output high force. Another advantage is that the interference effect of the pixels actually is very small, because you see here, in the connection part between the pixels actually is equiflex. So this equiflex has some cushion effect, right? It can will not, the vibration of each sensors, each actuator array will not be affected by each other. It means that we can output the pattern vibration very easily, right? Very easily. So this is totally different from the cell phone. Okay. Then why we need to output the pattern one? Why it can output more? It can provide you richer sensation. So but we have to say that, okay, this figures, my supervisor, Professor Lee in UC Berkeley, highly recommend us to, you need to figure out, okay, how to solve a very serious problem is that your driving voltage is still very high. It's up to 500 volt. Even though I have to say the power is not so high. So even there's some electrical leakage, it will not kill you, but may you feel a little hurt, right? A little hurt, a little painful. But if you, for customized electronics, this is the very, very serious drawback, right? Nobody want to be hurt by your devices, So is there any way to, further reduce this drawing voltage? Yes, we do some simulation, and this simulation is also done by Yuan. Okay. So we have find two ways to do that. So from the device aspect, the first one is increasing the charge density or dV value of the piezoelectric. Yes, that's true. If you increase more, you can reduce the drawing voltage. But that's a limitation. What's the upper limitation? Is that still going back to here? Actually, the device is somehow to a parallel capacitor, right? Two phase capacitor. So if you locate or increase the charge density here, finally the air will be broken down, and then you will lose all the charges. But so that's the upper limit. And another one is that, optimizing the device structure, just like reducing the thickness or something like that. It can also, reduce the drawing voltage. But also that's a limit. That's why I like actuator work, right? You need to find the balance. Okay, you need to consider the mechanical aspect, the electrical aspect. Then you find the balance. Then we can have the best output. That's why I think that actuator work is very interesting, also very challenging here. Okay, so if what's the limit of the reducing the thickness? So we need to provide haptic feedback. Yes, your vibration is strong. The amplitude is large, but your weight is very small. Then when you hit your skin, it still means nothing, right? Because it's too light. The weight is too small, right? The energy that can transmit through your skin is still very small. So that's another problem we need to solve. So we need to make the balance. We need to find the best point. So, but actually, no matter how, our final goal is that, okay, when the voltage is less than 10 volt, the output force, the peak output force can larger than 10 millinewton. Okay, this is our goal. And another aspect is that, okay, just what I say that, okay, actually, we need to deliver more energy, right, to the tactile acceptor to your skin, that you can feel the stronger sensation. So these aspects that, okay, we need to increase the output or optimize the device, and other aspects that we must reduce the waste, right? Yeah, your actuator can output very good. The output of your actuator is very good, but most of the output is wasted. It's not delivered through the tactile receptor here. It's not okay. So another way is to improve the energy transmission efficiency. If we work hard or do some efforts on these two aspects, we can improve the overall performance. What's the overall performance? Is that under low drawing voltage, you can feel high, or we can feel strong sensation. This is the overall performance. So the first step is that we must learn how you feel the tactile. Then we must make clear that what is the typical features of different tactile receptors under your skin. Just like we find that there are 4 kinds of tactile receptors. So this SA1, SA2 is for static signal, just like some tension, passion, or passing sensation. And this RA and the PC receptor, they are sensitive to the vibration signal. Actually, the first step is that we are focusing on these 2 receptors, but now my students are also doing some work that are focusing on these the other 2 kinds of receptor that can make you feel the tension or passing sensation. Okay, passing sensation. So we find that, especially for the RA, is good to sense displacement in small area and low frequency. And this PC is good for energy large area and high frequency. So in order to, how to say, specifically trigger this PC receptor, then we design such an contactor, mechanical contactor, that is called analog shape contactor. that can, this large area can trigger this one, and this small tube area can trigger RA. So with this way, we can make you feel the sensation better. Another one, we find that the heat load force is a very important parameter. Okay, when you apply a different heat load force, the sensation feeling is very different. So we can also how to study how you can need to study how to optimize the heat load force, optimize that apply on the actuator. So with this way, this is what we publish in Biosense and Bioelectronics. Actually, we submitted to Nature and then Electronics first, and then it's alpha review, and then we will assess. Okay, I don't care, your device. I care how you feel. So what your device can be done what your device do can be done by a piezo vibrator. So they reject us. Okay, but that's why I think this was very interesting. Okay, so here we design such a symmetry structure actuator. They are using two actuators working together and contact design. Okay, by using this way, we can lower the drying voltage about 20 volts. So in 20 volts, in the most frequent range, you can feel the sensation. In some specific frequency, because in this range, the human skin is more sensitive to such frequency. Another one is that this is the wavelength frequency. So actually, the drying voltage of our actuator is very small. When you compare to other reported works. Because the drying voltage of our actuator is so low. So this actuator can be directly, powered by two batteries, the two lithium batteries, connected in series. So the output voltage is just about 7.5 volt. Okay, 7.5 volt. By using this one, 7.5 volt. And here we use a very good demonstration is that, okay, we made everything to be wireless driven. Okay, you can use the wireless control module to control the vibration of the actuator to send the information to the user. So here we code the vibration signal is that when it's short vibration, it means left transmitting, and the left turn, and the long vibrating is the right turn. Because the coding strategy is very simple, so the volunteer can 100%, 100% recognize the vibration signal. So here, this is a video. Okay. So this is randomly generated signal. So it's telling left. Okay.
Left. Right.
Wireless haptic feedback system.
Left. Left.
Because this is randomly generated information, so he tried many lefts. Okay, this is right. Okay.
Right.
Okay, 100% right. Okay.
Left.
Yes. Okay. And then after this work, we are thinking, okay, yes, normal people need such haptic feedback, but how about other people just like disabled people? Maybe especially for the blind people, maybe they need this haptic feedback system more, right? They are more important to them. So in order to do some works for the disabled, especially for the blind people, so we developed such an actuator array. So this is a transparent actuator array with high output. Okay, and we do two demonstrations. The first one is the tactile assisted feedback assisted work navigation. Just we can program the vibration signal to means different information. Just like you fast increase, slow decrease means left. Slow increase, fast decrease means the amplitude. Okay, means right. If very sharp vibration means stop. And smooth vibration means you can go on. So this is just an example. Another one is that, okay, we can construct a 6-pixel actuator array. So what's this one? It's a 6-pixel that vibrate. This is stops, the actuator. Okay, 6 pixels actuator means what? It's a barrel, right? 盲文. A very interesting question. Why the barrel needs 6 stops? Why? Okay, because 6 level is what? Is 32, right? Right. Then we need, it can cover the 26 sorry, 64. Okay, so that's a little wrong. Okay, sorry. You can cover all the figures and English alphabet letters. Okay, alpha letters. So that's why you need the six stops here. 6 stops here. Okay. And by using this one, you can, by using this stops, you can, deliver the different haptic feedback, haptic information. Just like, so this means lean, this means lab. Okay, this means lab, because my professor is called lean, so called lean lab over here. Okay. And this is and the performance of such kind actuator is also very good. Okay, because now here we use such very good design here. We optimize the thickness and especially the height of this supporter. Then we can make this output force that can be larger than the vibration mode of the cell phone. Even the giant voltage is about 200, peak-to-peak giant voltage is about 200 volt, and it can output very smoothly. So here, the output force when divided by the giant voltage here, or the output force per giant voltage here, always the best work reported at that time. Okay, and this is a video for showing our demonstration is the navigation, tactile assist navigation with the actuator. So on the hand of this volunteer, actually the first offer here, we put an actuator and a very simple giant circuit. Okay, with this one, then we can finish this side pulse. So here, this is the giant voltage we record. Okay, and then now is the stop signal. Okay, means it's sharp vibration. And then the very smooth vibration means that, okay, you can go forward. Okay, go forward. And then make this volunteer to be stop. Okay. And 10 left. Okay, 10 left. Stop. Okay. Yeah, that maybe the information deliver efficiency is low, but remember our target user is bright people, right? The first priority is that help them to accurately finish the perfs. Yeah, actually this video is a little long. You take 2 minutes. So finally, the volunteer can go through the pulse to here. Okay, finally. We don't want to play through the whole video because somehow it takes a long time, but finally it goes to here. Okay. And okay, after introducing this actually, I want to introduce the work. I like this work very much. And also, we put a lot of time on it. It's a textile-based, all textile-based actuator that can provide you the haptic feedback. Also, is air permittable. Why we want to design such air permittable actuator? Because we want to ensure the wearable comfortability and output abilities. So we want to achieve more, because for wearable electronics, the wearable comfortability is also a very important feature, right? You need to pay attention. Here we also use the textile electrodes and the textile piezoelectric material to do that. And the air permittable ability of such actuator is very good. Just like also when you can blow through your head, when you can blow through the actuator, and then we can also make the frames moves. And actually the air permittable ability of our actuator, it can be compared to the normal kinds of textiles. And The output performance is also sorry, just not my okay, there's a pointer. So the output performance of our FML actuators are very good. Okay, here's a very interesting demonstration. We use it to construct a wireless wireless haptic sensing and actuating system. So we also use the sensors, the tactile sensors, to the as the sensor graph, and the actuator graph is composed of our actuator here. And this this sensor, this system can walk up to a distance of 100 meter away, and it can here, because we have only 5 sensors here, right? 5 sensor is 5 level is actually is 32. Okay, 32. So we can cover all the English letters, and we also have other just like some symbols here. Then we can use the sensor graph to code the vibration, and then the actuator graph can distinguish the haptics information, just like you can code I-IWEAR, and then the actuator graph can deliver the haptics information I-IWEAR to the user. So this is a video, but this is not this kind, and it's another sentence. Is I apologize. Okay, really okay. Yeah, it's coding, and this filling into nothing. Okay.
A P O L O G R D E. I apologize.
Okay.
R E A L L Y question mark. Really?
Yes. By using this one, okay, we can successfully transmitting continuous haptics information, just like a sentence to the user. Okay. And also, because it's made of textile, actually we can make a very large part of actuator, just like this is actuator is 10 by 10 centimeter. It can provide haptic information for parts of human body. It can cover your whole body. Yes, chest is vibrating. Okay.
Right arm.
Yeah.
Left arm.
Yeah. Here, I want to emphasize that because here the pit low is very low. Okay, just it's very good for variable application. Okay. Yeah, this is the for covering different parts of human body. And so actually for our research goal, especially for the sensors actuators, this is our map. I draw, the draw. Okay, we want to make the digital human in metaverse be more real, or we want to communicate with the digital applications. Okay, more real, or what we call virtual environment to be more real. In order to achieve such a goal, right, we need the interactive multiple sensing system. Also, we need the haptic feedback system here. So this is our final goal. Actually, the virtual environment or metaverse somehow maybe is maybe the metaverse now they are failing. Right? They are failing. But I think digital tendency is also a very important development tendency of our country. So we want to, especially for the hardware part, we want to contribute our work. So this is variable sensing and a trading system for human machine interactivity. This is our final goal. Okay. And after talking about the sensors and actuators, and then I want to talking about more interesting idea is typical application of actuators is soft robotics, or we call electron insects. Okay, I will introduce very, very quickly. Okay, so here this is the first work is we introduced it publishing Science Robotics in 2019. So here we inspired from the cockroach. Okay, then that's a sentence. It's called Chinese. It's called 踩不死的小强. So this cockroach can stand brain about 1 million times of the self rate. So this is very interesting because the structure is very simple, and okay, here's a video showing it. So when you step on the cockroach, it's about 60 kilo brain. It's still hungry. It's still hungry. Okay. Another one is that our robot, by optimizing the robot design, especially the curvature of the body and the angle and length of the leg, we can make and dry it under resonant frequency. We can make the soft robot with the related very high moving speed. It can up to about the relative moving speed. It can up to about 20 body lengths per second. So here, when this was published, actually is the fastest soft robot moving speed in the world. So higher than the real cockroach and other kinds of soft robotics in such a scale. So this is a video for showing how fast it moves. So this is about 15 centimeters. Okay, when 1 second you can go through it. Okay, and also it has some very interesting performance, just like in kind of slope. Right, and just like cockroach, right? A cockroach, and it can carry some load, just like a peanut. But if you see this video, there's very serious drawback is that you can see that our robot, just run randomly. Okay, the direction is uncontrollable. So in order to solve this problem, and in two years later, then we publish another work in Science Robotics, and then in here we add two electrostatic legs on it. Okay, so actually we are inspired by the tending mechanism of the animals. So when you walk, actually you don't twist your joint. Actually, you just made the friction force between the two legs to be different. Then you tend. Then here we can you can add by these two X. Okay, you can act the electrostatic potential between the ground and the leg. Then you increase the friction forces. And then how we do that? Just that we just how to realize such strategy is that okay, we just collect the necks to the electrodes of the main body. Then we can use two wires to realize the tending. So how we can use two driving signal with 180-degree phase difference to drive it, and then we can adjust the bias of these two voltage that can control the electricity force between the ground and the foot that can make the tense. So with this one, we can realize very complicated motions, just like we can make it an L3 or just counterized rotation, counterized rotation, and 180-degree U10 or something like that. So the tending performance of our soft robotics is very high. It's also the highest the tending performance of the reported soft robotics. And then here you can in order to make you see how fast it can tend, then we compare the tending performance of cheetah. Right, this is a hunting cheetah. So if you shrink the device of the cheetah up to our size of our robot, okay, they are very similar tending performance. Just just exactly go along the obstacle. Okay, obstacle. And in order to more make how we can control the moving trajectory of our robot. Okay, so we may go through a maze. Yeah, and in order to make it some potential application, then we made a soft robot carry a very MEMS gas sensor to detect the leakage. This is a tube, tube composed of the LEGO. So this is a leakage point here. So we can control the robot to navigate the route, and then we caught the gas concentration map. So when it goes close to the leakage point, right, and then the gas. Good. Then actually after we publish it, after we finish this work, we submitted to a lecture science robotics, and the reviewer says that okay, now you still need to supply the power with 2 cables. Actually it's still not so useful. Can you integrate everything together, including the power, including the driving circuit together, and then you can make an entire version of soft robot. So and I say that yeah, we have a try. Then we integrate everything together. So we made a robot, carry a payload up to about 1.66 gram. Actually, most of the weight is contributed by the battery. The battery is about 1.5 gram. So how to control the moving trajectory? Here we use a 2 photo resistor here. So we connect the photo resistor with the voltage output, and then when the laser spot is on, is applied on the photo resistor, then this photo resistor is through, right? The resistance is reduced, and then the voltage can apply on the foot. So by using this one, we can control the left hand and right hand of this kind of entire version of soft robot. So this is the video for showing it. Okay. So when this soft robot video problem. So here, when we again, so when you carry it, it can still walk, run, go, and then but the speed is reduced. Okay. But in this way, we can use the laser to control the moving trajectory of such robot. So now first it moves directly, and then so it's something wrong with the video. Okay, so when you laser point is applied on this leg, it turn right, and the laser point it turn left. Okay, so our final goal of this soft robotic is that we want to develop some smart tiny soft robotics for sensing environmental informations, especially for the rescuing and searching missions, just like in some very complicated environment, just like the environment after the earthquake. So the environment after earthquake, actually it's very complicated, right? There are some many narrow spaces that normal sensors or rescue equipments cannot go. So if we can develop such small tiny robot, okay, it can go anywhere the human or traditional devices can go. Then we can save a lot of human. Okay. Finally, this is a long talk. Okay. Because this I prepare 1 hour talking slide. Okay. So finally, our summary research. So we actually focus on 3 application scenarios, assistant of Internet of Things, including wearable electronics, smart system, and soft robotics. So here is based on the electromechanical sensors and actuators. And so I want to acknowledge the institutes I have ever stayed, HUST, Berkeley, VIII. VIII is you guys know where is VIII, right? 理化学研究所啊，小宝方晴子听过没有？不听过。Okay. So and also some funding support from FDCT and SFC. And I want to acknowledge the professors I collaborate. Professor Li Weilin in UC Berkeley, Professor Takao Somaya in University of Macau. He is my supervisor when I was in VIII. Okay, and of course Yuan in Polytech, PolyU, and also other professors. If you want to know more information about my research, you can just search my personal website. Okay, and also I want to do some advertisement because I have some mission. Okay, maybe Qiu Tong can take a picture for me. 帮我照个相。Okay. So I was editor board for two national journals. The first one is advanced powder material that is held by Zhongnan 大学 Southwest University. Another one is Another one is nano research energy that is published by Tsinghua University. Okay. And also, my talk is over. Any question?
For the haptic feedback actuator, people may need some preload when we push it and to give the feedback. But for now, if for example, if you use the FEP or PVDF, it may soft and generate a very small
Yes.
force. So do you have any inspirations to me to how to solve this preloader requirement?
Yes, I think yes, I'm thinking about also thinking about the preload problem. In order to solve this problem, first one, you can apply some preload on it. I think another way to simply solve it, just increase the tension, right? You increase the tension, actually somehow the effect is similar to apply the preload on the actuator, and that's another drawback for applying the tension is that we reduce the flexibility. So how to make everything to be perfect? I'm still thinking about that. Actually.
Thank you.